In the previous lessons, we learned about ionization energy. Today, we are going to look at evidence of ionization energy, and we can actually see that in our experimental data. But first of all, let's talk about energy. Energy is equal to H times V. Now, H is the Planck constant, which equal to 6.62 times 10 to the negative 34 joules second. Then we have V in terms of frequency. Now, we're going to talk more about that later. Now, let's change this equation a little bit by substituting V with speed of light and lambda, which is the wavelength. Well, how is that possible? That is because c, your speed of light, is equal to lambda, which is the wavelength, times frequency. So therefore, V is equal to c over lambda, or the wavelength. Why do we care about this? That is this right here, this wavelength. It is something that we can manipulate easily in a lab. So wavelength is something that we can control, we can manipulate, we can change, so that we can see how does that relate to energy. And the word is change, okay? Change and manipulate it, okay? Keep that in mind. And of course, the speed of light will always remain the constant values of 2.998 times 10 to the negative 8th meter per second, okay? Now, with that information, how is this relate to your test? Well, I can ask you a question about a certain thing. How does energy relate to frequency? If I increase V, guess what happened to energy? It will also increase as well. So let me change color. So if I increase V, guess what happened to the energy? It also increased. But what happened when I increase lambda? Let's change to a different color. What happened when I increase lambda wavelength? What happened to the energy in this case? Well, look at this. The wavelength is on the bottom. So if we divide by a larger number, this number is going to decrease. You see how that works? And why do I care about H and C? Because those are two constant values. Now that you have learned how energy is related to frequency and wavelength, let's talk about the experiment that's actually supporting this concept. There is something called a photoelectric effect. Photoelectric effect is basically saying that these are actual evidence collected in our data. Okay, it's basically support that light exists as both wave-like and particle-like. And wave-like, it looks something like this. It looks like wave. Think of the wave in the ocean. And if we look at term of frequency, if this compared to this right here would be high V. That's high frequency. This will be low frequency. And this will be low V, okay? Well, let's look at particle light. Well, think of the word particle. Well, particle just basically like that. Just like an atom, okay? And we have a specific name for this particle of light. It's called photon. So the evidence of photoelectric effects support that light or energy exists in form of wave-like and particle light. Now let's talk more about photon in terms of the photoelectric effects. Basically, it showed that light in form of particle called photon with enough energy will cause metal to eject electron when the light strikes on the surface of the metal. Here I have the metals right here on the surface of metal, and if I have different form of light, let's look at this diagram right here. Here I have my metals right there. What I'm going to do is I'm going to use different light at different wavelength, which again indicate the level of energy. Let's look what happened when I decrease wavelength. Notice how this one's 700 and this one's 500. If I decrease wavelength, the energy would go up, which means more energy. And what happened is this: the electron get ejected from the metal surface. So that means if you have a photon with a right amount of energy or enough energy, it will cause the metals to eject the electron. And that's important because now we can measure the velocity of electron. And then we can actually study more about the structure of an atom. And then we can summarize all those information into this one short equation. It's basically incoming radiation equal to binding energy plus kinetic energy of the ejected electron. And the incoming radiation is a different light that we use to shine on the piece of metal. Because different light will have different energy, okay? Because different light at different wavelength will have different energy. So incoming radiation And we know that energy is conserved in this whole entire process. Whatever energy you input in will equal to the energy put it out. So in this case, we have binding energy, and the word binding, think of electron bind to an atom nucleus, okay? And we call that ionization energy as well. So binding energy is another term for ionization energy. Now, because the energy is used to break this electron from an atom, it's a kinetic energy, is the energy of motion. Now, in terms of motion, the faster it goes, the more kinetic energy it has. So why is that important? Well, we mentioned that energy is conserved. That means it doesn't change. Whatever you input in will be output out at the same amount of energy. In this case, we have two things that's happening in this equation for the output. We have binding energy, is the energy required to remove the electron. Then we have kinetic energy. So any energy that is not used to break the electron free from the nucleus, okay, that's energy, and that's left over will be converted to kinetic energy. So you have incoming radiation with a lot of energy, and those energy will be used to break the electron free, and the leftover will be converted to kinetic energy. So how is that important? And with that information, we can now explain that electron that is further away from the nucleus will require less binding energy. That makes sense. If it's further away, the electrostatic attraction between them will be very less. So therefore, it will require less energy. And if it requires less energy, the leftover energy will be what? Will be converted to kinetic energy. So therefore, electrons that are further away from a nucleus will therefore move faster, okay? And we can actually detect the velocity of each electron that's being ejected from the surface of metal. And that's how we use the information from photoelectric effect to understand that electron is related to energy, and that energy is related to wavelength and frequency of light.